Hi, this is John Whitaker for the Probability 1 class, and this is our 29th video lecture. And today we want to do some work on Chapter 4, beginning Chapter 4, which has to do with Markov chains. So we're going to go ahead and get started with what a stochastic process is. A stochastic process was defined in Chapter 2, but I didn't define it for you in the video lectures, and so let's do that now. Here's the definition. A stochastic process x of t, with t being an element of an indexing set t, is a collection of random variables. That's all. And as a comment, in a stochastic process, t is often interpreted as time. Now I want to list several definitions, and they're all prefaced on, given a stochastic process, and let's label that stochastic process. X of t, with t being an element of an indexing set. First definition is that t, as I have been saying, is called the index set of the process. B, if t is countable, x of t is called, well, I should write it as the process. X of t is the t element t is called a discrete time process. C, if t is an integral of a real line, then x of t, t being element of t, is called, or said, to be a continuous time process. And lastly, the state space of a stochastic process. Is the set of all possible values that the variable, or that the variable, the random x sub t can assume. Let's look at an example. Let's let x sub t, so t is known with t, be the stochastic process of the number of videos watched over probability course T days into the class. Into the course. That's right. With t being an element of 1, 2, all the way up to 30, let's say 3. And x sub t for a fixed t has domain. I'm sorry, this should go all the way up to 72. Yes. I think it was 76. That's what it was. Yes. That's the days, okay? And x sub t for fixed t has domain the set of students in the course, and range let's say 1, 2, 3. Here's where I should look at the camera and say 33. So that's how many videos I think we'll get to. Something like that. Which are the number of videos for the course. Then this is a discrete time process. at another example. We'll let x sub t, such that t is known of big T, be the stochastic process of the price of stocks listed on the New York Stock Exchange at time t since the opening bell. That's when they start trading stocks per day. On July 17th, where t is known from 0 to 8. That's any number in between 0 and 8. I'm thinking that the stock market's open for 8 hours, so t is representing the time since the opening bell. An hour. Then, x sub t, the t element of big T, is a continuous time process. And for each t, okay, x sub t domain is the set of companies on the New York Stock Exchange. Okay, so that's in general a stochastic process. Now we want to move on to what a Markov chain is. So here's its definition. Let x sub n equals 0, 1, 2, whatever, be a stochastic process that takes on a finite or countable number of values if x sub n sub I or x sub n is equal to I, then the process is said to be in state I at time n. Okay? If when defined, the probability of x sub n plus 1 given, or equals to j, given, I'm going to write this slower. Given x sub n plus 1 equals to j, given x sub n equals to I sub n, and x sub n minus 1 equals to I sub n minus 1. X sub n minus 2 equals to I sub n minus 2. All the way down to x sub 0 equal to I sub 0. is the same thing as the probability of x sub n plus 1 equaling j given x sub n equals I sub n. So these other given conditions really don't play any factor at all, just this one in the process. Then, this process is known as a Markov chain. Okay, so that's what I'm defining really as a Markov chain. Okay, in terms of some notation, the probability that x sub n plus 1 equals to j given x sub n equals to maybe I, that can be denoted as probability of p sub ij. And p sub ij is called the transition probability from state I to state j. And the idea is for a Markov chain the conditional distribution of any future state we'll call that x sub n plus 1. Maybe I should say for the next future state. We'll leave it as it is. Given all the past future states, all the past states, future states, x sub 0, x sub 1, all the way up to x sub n. Let's say x sub n minus 1, and present state x sub n, so this is x sub n minus 1, is independent of the past states and only depends on the present state. Some facts. P sub ij has to be greater than or equal to 0, for it's a probability. could also say it's got to be less than or equal to 1. And then, another fact is that the sum, so this is fact, part A, and the sum, as j runs from 1, well, whatever it runs over, of p sub ij, that has to be equal to 1 for fixed I. And this is true for all I. Okay? But if you fix an I, you let j run, you look at those sums, those transitional probabilities, you got to get 1. Okay. Notationally, our notation, the book will adopt a policy that usually, for a Markov process, x sub n, where n equals 0, 1, 2, forever, we will consider the possible output values x sub n to be the set of non-negative integers lots of times we'll do 0, 1, 2, 3, whatever. Now, in terms of another definition, we let x sub n equaling 0, 1, 2, forever, be a Markov chain. Then we're going to define a certain matrix. Script P equal to P sub 0, 0, P sub 0, 1, P sub 0, 2, forever like this, P sub 1, 0, P sub 1, 1, P sub 1, 2, forever like this, and forever like this, and maybe we have P sub I, 0, P sub I, 1, P sub I2, forever in this direction, forever down. That, well, however it goes, not forever, but, oh, maybe forever, yeah, forever, could be. This is called the matrix of one-step transition probabilities the matrix of one-step transition probabilities P sub ij, or I like to call it the one-step transition probability matrix. Okay. We're going to look at two examples, and that will conclude the lecture for today. So in the first example, we suppose that the chance of rain tomorrow depends by the way, this example is something from the book. It's on page 192, okay? So suppose that the chance of rain tomorrow depends on previous weather conditions only through whether or not it is raining today. And not on past weather conditions. Suppose also that if it rains today, then it will rain tomorrow with probability alpha. Okay? If it does not rain today, if it does not rain today, it will rain tomorrow with probability beta. Okay? Find the one-step transition probability matrix. Okay, it's not a very hard problem. Okay, so we need to kind of clarify what's going to be our representation of this situation through a Markov chain. And here's what I'll tell you. This is a Markov chain. And for me, it's easy to see that this is going to be a Markov chain. In that it's x of n, so n is equal to 0, 1, 2, wherever. Okay. That has only two states, say 0 and, or 0, I'll say, when it rains, and 1, I should say when it rains today. And 1 when it does not rain. Okay. The reason I said it was kind of clear to me that this was a Markov chain is because it clearly states in the problem that what it does in the next day doesn't depend on more than what it did the previous day. Okay, it just depends on what the weather was like the previous day. Okay. Now, in terms of getting these transitional transitional probabilities, here P's of 0, 0. Okay. What is that? That's the probability of x of n plus 1 equaling 0, given x of n equals to 0, and that's the probability that it rains tomorrow, given that it rains today. And in the work, in the problem, it says that's alpha. Okay. Now, the probability of 0, 1, that's equal to the probability that x of n plus 1 equals to 1, given that x of n equals to 0. Writing that down in words, it's the probability that it does not rain tomorrow, given it rains today, and what that's going to be equal to is 1 minus alpha. Okay. And that's from that part B factor we had. Now, the probability of 1, 0, that's the probability that x of n plus 1 equals to 0, given x of n equals to 1. And that's the probability that it that it rains tomorrow, given that no rain today. And that was defined to be equal to beta in the problem. Okay, finally, the probability of the piece of 1, 1 equals to the probability that x of n plus 1 equals to 1, given that x of n equals to 1. And that's the probability that it doesn't rain tomorrow, given that it does not rain today. And that's equal to 1 minus beta. So, the one-step transition probability matrix is P equal to alpha, 1 minus alpha, beta, 1 minus beta. Okay, we want to look at another example. Suppose that whether or not, this is an example, it's on page 193 of our text, whether or not it rains today, is dependent on the previous conditions through the last 2 days. Okay. And here's the specific information. Suppose that if it has rained for the past 2 days, then it will rain tomorrow with probability 7, or 0.7. If it has rained today, but not yesterday, then the probability it will rain tomorrow is 0.5. fine. If it rained yesterday, but not today, then it will rain tomorrow, with probability 0.4. Okay? If it is not rained, in the past 2 days, then it will rain tomorrow with probability 0.2. Okay. And then what we're looking to do in this problem, given all this information, is it's form a Markov chain to represent this situation and give the one-step probability matrix. Okay, here's the solution. First thing in terms of the solution is I'm going to say something in the solution in comparison to the previous problem. And that is, if we define y sub n to be equal to 0 if it rained today, and y sub n to be equal to 1 if it did not rain today, then y sub n equals 0, 1, 2 is not a Markov chain. So let's take a look at why. Okay. So here's the reason why. If we start off and say, well, no, 0.7 is equal to the probability that y sub 2 equals to 0, given that y sub 1 equals to 0 and y sub 0 equals to 0. Okay, so this is saying, hey, look, the chance that it rains tomorrow, given the chance that it didn't rain tomorrow, given that today it didn't rain and yesterday it did. Okay, so we're starting. I'm sorry. the chances that it rains tomorrow, given that today it rained and yesterday it rained, that's 0.7. Okay? Now, if y sub n equals 0, 1, 2 was a Markov chain, then that would tell us that the probability that y sub 2 equals 0, given y sub 1 equals to 0, because that's supposed to be the same thing, is equal to 0.7. Okay. Also, we have that 0.5 is equal to the probability that y sub 2 equals to 0, given y sub 1 equals to 0, and y sub 0 equals to 1. Okay. So this says that the chance that it rains tomorrow, given that it rained today but not yesterday, that's equal to 0.5. But that would be equal to, if it's a Markov chain, y sub 2 equals to 0, given y sub 1 equals to 0. And that's a contradiction. So we have that 0.7 equals to this probability, and it's also equal to 0.5. But it can only be one number. This is a number. That's a contradiction. So it can't be a Markov chain. It's not a Markov chain. Now, here's what we can do. We can, instead, to represent this situation, define x sub n, what happens on that, to be equal to 0 if it rained today and yesterday. Rain today and yesterday. So that's 0. Okay. X sub n equals 1 if it rained today but not yesterday. X sub n equal to 2 if it didn't rain today, but rained yesterday. And x sub n be equal to 3 if it didn't rain today, and it didn't rain yesterday. Okay. Now, here's what I want to say. Because the weather tomorrow is only influenced by today's weather and yesterday's weather, that means that these x sub n's that we've defined, with n being 0, 1, forever, is a Markov chain. Okay? And in terms of, we're running out of time, but in terms of its transition, one-step probability transition matrix. Okay, so here, let me start off with P of 0, 0. That's equal to the probability that x sub n plus 1 equals to 0 given x sub n equals to 0. And that's equal to, so let me go through this. That's the probability, I only want to do a few of these. The probability that for 0 means it rained today. So that would be, it rains tomorrow. And today, given it rains today, and yesterday, okay? And so this is the same thing as the probability that it rains tomorrow, given that it rains today and yesterday. And that's equal to, the problem set is 0.7. Okay, so that's one of the answers. Okay, let me look at one other. We can go through all 16. This is going to be a 4x4 matrix. It's going to have 16 entries. But I'm going to do a few here. So the next one, the probability, the piece of 0, 1, and that's equal to the probability of x of n plus 1 equals to 1, given that x of n equals to 0. And that is equal to the probability, okay, that it rains tomorrow, but not today, given that it rains today and yesterday, but that's equal to 0. Okay? And the reason that that's equal to 0 is because you're saying it rained today, and here you're conditioning on that the event that it rains tomorrow but didn't rain, but not today. So, I mean, if you know that it rained today, it cannot be clear today as well. So that's 0. And then the probability of 0, 2, this will be the last one I do. That's equal to the probability that x of n plus 1 equals to 2, given x of n equals to 0. And that's equal to the probability that it didn't rain today, did not rain tomorrow. And it rained today. Given it rained today and rained yesterday. And because this is the complement of p sub 0, 0, then what we have here is this has got to be equal to 0.3, 1 minus 0.7. I'm going to stop there and just in terms of these individual calculations. Did I not turn this? Okay, look, I went through some more of these one-step transition probabilities, okay? So here's what's listed. I'm sorry, I was talking about it. I got to turn it, I guess. Well, what I'm going to end today with is just here's what the one-step transition probability would be. It's 0.7, 0, 0.3, 0, 0.5, 0, 0.5, 0, 0, 0.4, 0, 0.6, and then finally 0, 0.2, 0, 0.8. Okay, that's enough for this video lecture. Thank you very much.